Hi, everyone. Here we're going to be talking about covariance and correlation. So we're going to cover covariance, correlation coefficients, correlation and causation, and correlation matrices in pandas of Python. First, covariance. Covariance refers to the joint variability of two variables. And two important components here, joint variability and two variables. So it's usually only two variables that we're discussing, and also the joint variability. So in a classic example, height and weight of individuals. And you can see here a graph representing that, the height on the x-axis, the weight on the y-axis. And the covariance is how these two variables move together. Also notice that this usually assumes paired data. And by paired data means that the two variables are of the same entity. So here, height and weight, this first one here, is of the same row, is the same individual. And the second one too is the same individual that has a height and that individual's weight. It's not just some height of some people in Indonesia and then some weight of some other people in Guatemala. It's not going to make any sense doing that. So let's remember this paired data. Covariance functions provide a measure of this joint variability. So the function or the formula provides a measure of this joint variability. And here's the formula. It's pretty straightforward, actually. So it's the sum of the product of the differences between each data point. So this is each data point minus the mean of that one variable. So let's say the x variables times the difference of each data point to the mean. This here means the mean of that other variable. And you sum those differences and you divide by n, and you get this number that indicates covariance. The sample covariance, so this is for population when you have actual population data. When you have sample data, it's the same idea, but there is this -1 here for the degree of freedom, and that helps actually get accurate numbers. And there is positive covariance. So when it's the two variables at question move in the same direction. So this is the one right here. So if this calculation here, if you were to do it with this data, if you were to plug in all these numbers, you would see that the value would be greater than 0 from this covariance. And that means we have a positive covariance, which means that the numbers move in the same direction. As one goes up, the other goes up. Negative covariance is when the two variables at question move in opposite direction. So that's this one over here. And that if you were to plug in the numbers for that, in this case, it would be greater than 0. But if you have a negative relationship, there would be less than 0. And there will be roughly equal 0 if there's no relationship. Notice also that we're talking about ordinal, ratio, or interval data. So this is not categorical data, not nominal data. We cannot compute this information with categorical data. Correlation coefficients. Correlation coefficients are a normalized measure of covariance, and that's what we usually use in practice. And they provide a more precise strength of the relationship between the two variables at question. And the standard correlation coefficient is called Pearson correlation coefficient. There are other ones, and there's some details on the actual measurement of the statistic, but this should be sufficient for us for now. And the formula is for population. Notice this P here is rho, and this is a symbol for Greek letter for correlation coefficient. So the correlation of x and y equals the covariance of x and y divided by the standard deviation of x times the standard deviation of y. So if you are interested in the math, you can look deeper into it a little more to see how that works. And we were just looked into the covariance, but then we just divide that by the product of the standard deviations of each of the two variables we measured. The sample is essentially the same thing, but there's some small variations when we're dealing with sample data versus the population data. Here's going to look kind of identical, but it's broken down. This is, once again, if you can see, xi is each of the points minus the mean of x times the same calculation for the other variable, and then divided by, this is the formula for variance and standard deviation, as we have seen before. And the R is used here. So rho and R are used for the symbols for correlation coefficients. So a correlation coefficient is a number, rho or R, between -1 and 1. So negative rho is negative correlation. So these two over here, this one is perfect negative correlation, rho equals -1. Here is slightly negative correlation, so it's between -1 and 0. Here, rho is positive correlation, so the number is between 0 and 1. This number is just, this is, I'm not sure if this doesn't, oh, this could be perfectly correlated. So rho equals +1. And then if it's kind of all around, then rho is 0 or near 0. We have a table over here. Well, what about 0.3? So it's kind of obvious, 0, no correlation, -1, perfect correlation, +1, positive, perfect correlation. But what about 0.3? What is that? Is that weak, moderate, strong correlation? And of course, it depends. So it depends on the context you're in, it depends on the expectations, it depends on what's at stake. If people's lives are at stake, then maybe 0.3 is pretty serious correlation. And you may want to get something checked out if it has to do with a disease that is correlated with some actions you're doing or with some surgery. Sometimes correlation of 0.95, which is generally very high, but if it includes, once again, how well a car operates in snowy conditions, and people may die as a result of something less than perfect, then you may also want to consider that not strong enough. Sometimes the context involves a lot of people, so even a small correlation of, generally considered a small correlation of 0.16 would impact millions of people. But so it could be sort of significant in a contextual sense. Correlation matrix. A correlation matrix is a table of the correlation coefficients between all variables in a data set, and it's a very useful way to as part of exploratory data analysis. And this is one nicely visualized here with additional information with the color scheme here, indicating which ones are very strongly correlated, and the ones that are more neutral is kind of near 0, and the ones that are more reddish and dark are negative, bluish and dark positive, and so on. So what does this mean? So in this line over here, because each of the variables are repeated. So for example, if you have various variables here, this is referring to surveys regarding different types of computers and how well people appreciate them. So we have iPad, iPhone, iPod, and so on, and you have the same variables listed here, the same variables listed here, and the same variables listed here. So iPad, the way people respond to survey on iPads is perfectly correlated on the way people respond to surveys on iPad. That's why it's 1 here. This is why it's 1. But iPad and iPhone, so iPad actually would be iPad here, and iPhone is actually mildly correlated, 0.22. So the way people respond to iPad is positively correlated with the way people respond to iPhone. Okay, but the way people respond to iPad is not correlated with the way people respond to their preference for PCs or non-Macs, slightly negative, but almost negligible. So that's how we understand these here. Correlation coefficients may also calculate statistical significance, which helps with causal inference, and that's a step above the exploratory data analysis that helps us confirm that the correlation is really strong and may indicate some causation. We were not going to do that at this stage, but we will do that next time. And here's, well, you may see the correlation coefficients between their variables. There's a correlation matrix, again, from another study. And then they also calculate significance level. And that is because, for example, usually the higher the N, the higher the sample size, you can have more guarantee that your correlation will apply to the population, and therefore we would say it's statistically significant. We'll explore that a little bit more next time. So next up, we're going to be talking about correlation versus causation.